Hello everyone, am I audible to everyone?
Yes.
It's fine, perfect. There's no need to take off the mask. Great. First of all, can I request each one of you to please mute your mobile phones during the conference? Yeah, thank you so much. So, good morning to all of you. On behalf of all of us at ISET Thiruvananthapuram, I would like to extend a warm welcome to each one of you to a beautiful campus nestled amongst the forest and foothills of the serene Western Ghats. Although we've been going through a lot due to the ongoing pandemic, I hope all of you are very excited for the 4th BRICS Mathematics Conference, as much as we are hosting each one of you in our institute. So without much further ado, I would like to invite Professor Vijay Thomas, Professor and Head of the School of Mathematics at ISET Thiruvananthapuram, and a member of the National Organizing Committee of the BRICS Mathematics Conference. So may I request you please come on stage and share your thoughts?
Thank you, Adya. A very good morning to all of you. First of all, I would like to say sorry that we are about 10 minutes late. But anyway, I'm sure that we will be in time. First of all, before saying anything, I would like to thank our director who has extended all support for the conference. He was instrumental in bringing the 4th BRICS conference to our institute, along with Professor Meena Mahajan. And funding was hard to come by during the pandemic, but he was very supportive and he extended all support, because of which everything is going, I hope, will go smoothly. It is, everything is I mean, we are all ready for it. Hopefully nothing goes wrong. I would like to say something for the participants who are online. I actually feel a little sorry that you are not here because you are missing a very beautiful campus. You might have Googled Kerala and it is said God's own country. And I would like to say that our campus within God's own country is God's own garden. We are located in a very beautiful place. I'm sorry that you are not here. I also feel sorry for ourselves that you are not here because we could have interacted with you. Our students could have interacted. This chance has been lost because of COVID. So I feel sorry for that. But I'm still very sure that it will be a very fruitful conference. Lastly, I would like to mention that the conference is almost fully organized. All the hard work is done by the Club of Mathematics of ISET Trivandrum, and they have worked very hard for this conference. And I also want to thank everybody else who has helped for the conference. The cover page, everything has been designed by our own students. So we are very proud of that, and thank you to them. Finally, I would say welcome to all from ISET TVM family. I hope we will have a very fruitful conference, and I am very positive that it will be a very fruitful conference. Thank you.
Thank you so much, sir. I am now delighted to invite Professor Meena Mahajan. She is the professor at the Department of Mathematics at the Indian Institute of Technology, Mumbai. That's IIT Bombay. She is also the Dean of Faculty Affairs at IIT Bombay and a Senate member of ISET Thiruvananthapuram. Lastly, she has been a member of the core committee of the BRICS Mathematics Conference for the past 4 years. Ma'am, can you please come on stage and share your thoughts?
Am I audible? So good morning, good afternoon, good evening to the different people who have joined this conference, and welcome to all. On behalf of my fellow core committee member from India, Professor Balasubramanian, scientific committee members, Professor Sudhir Korpade, Professor Maithili Ramaswamy will be joining us soon, and Professor Devashish Kundu, and the National Organizing Committee, organizers from IISER Trivandrum and PML Munjar University. It gives me great pleasure to extend a very warm welcome to all of you to this hybrid mode BRICS conference, 4th edition, conducted in IISER Trivandrum from December 7th to 10th, 2021. I have a small presentation. Okay, so this BRICS mathematics conferences started roughly around 5 years back. So this is an annual conference which is aimed at strengthening cooperations and exchanges in the field of mathematics among 5 BRICS countries. As you know, they are Brazil, Russia, India, China, and South Africa. So the first BRICS conference was held in Beijing, China in 2017. The second one was in this beautiful waterfalls of Iguazu in Brazil. And the third one was held in 2019 in Kazan, in Russia. So this is the 4th edition, which we had initially planned in July 2020. Unfortunately, because of the pandemic, we could not really go ahead with this. So finally, we thought at least we wanted also, right from the beginning, we wanted to use this as an opportunity for a national conference also. And that was the idea of having everybody and having a huge conference. Unfortunately, this is what we can offer right now in a hybrid conference because of the pandemic and new editions of pandemic. So this is a fantastic idea of a logo which has been brought by the local organizing committee. So this logo has been designed by Club of Mathematics IISER Trivandrum. So this is motivated by the metafoil knots with the crossing number 5. So every path in this knot represents a color that represents each of the 5 BRIC countries. This is a fantastic logo, and I would like to propose this as a conference BRICS logo for all the BRICS conferences in mathematics. So thank you, Maths people, for doing this. So about this conference, we have a series of 15 plenary talks, 3 from each of the BRICS countries, 16 invited talks, and 37 contributed talks. As you know, the conference will run in a hybrid mode with all the events streamed on a corresponding Zoom room for all 4 days of the conference. So the online participants can be part of the talks by joining us through Zoom. So all who are here must have got this booklet with different color codings, which are easy to understand, representing different kind of talks and also the countries and so on. The talks are divided, classified, conference locations are given in this booklet. So please spend some time. This is also a very nicely designed booklet. So I think at least people who organize conferences should carry a copy with this, because this can serve as a guide for organizing future conferences. Yeah, so coming back, if you look at this, the way in which the color coding, minutest of the details are taken care of is really very impressive. Yeah, so any IT support you need, this is the address. And maybe you can note down the login details for this room, for instance, is username is BRICS and the password is BRICS@ISA-TDM. We don't encourage you to use this during the conference, but just in case. Yeah, now I want to acknowledge a few people over here. So first of all, let me start with how this idea came up. So Professor Sudhir, Professor Maithili, and I were in Russia for this Kazan 3rd BRICS conference. At this point, we were told that we have to organize the next conference in India. So all it took was a WhatsApp message to Professor Murthy and Professor Manoj Arora from BML Munjal, Vice Chancellors and Director, who enthusiastically agreed for hosting it in their campus. And I should say, in all this difficult times, they have been supportive throughout. In fact, for July 2020, BML Munjal had organized the travel for all the foreign speakers for the conference. Unfortunately, all of that had to be cancelled. And there have been, I said to Trivandrum, when we knew that we are not going to have this conference in the normal scenario, and funding agencies stopped giving us giving funds for any conference. Both of them were always, both Professor Murthy and Professor Arora were always supportive, cool, and then they said that, okay, go ahead with the conference, don't worry about the budget. So I'm really, really very thankful to both of them. The other point which they were stressing is more than BRICS, they wanted to focus this as a national conference. And this is really something which is commendable. And I find it as an opportunity to meet all mathematicians who could come here, at least all people who came here. We are all meeting after almost 2 years. So this is a great opportunity for us. So thank you, sir. Thank you, Professor Arora. Then in the last moment, since no funding agency was providing us with funds, we approached the mathematical community who organized ICM 2010 conference, and they provided us with the generous funding in no time, probably a couple of days time. The money, the sanction was granted. So I am very thankful. Professor Godpade has been instrumental in doing this. Thanks a lot. I would like to thank all the speakers and all the participants who actually agreed to come here also and also speak virtually. And math colleagues who were very supportive all the time, and all the participants who are joining this conference. Thanks everybody. Enjoy the campus, enjoy the conference, follow COVID protocols. Thanks.
Thank you so much, ma'am. It is my pleasure to now invite Professor Anirban Chakravarti. He is a professor at the School of Engineering and Technology at BML Munjal University. He is also the Dean of Research at BMU. Professor Chakravarti is here on behalf of the Vice Chancellor of BMU, Professor Manoj Arora, who is unable to attend this event. I would like to inform all of you that the 4th BRICS Maths Conference is jointly organized by ISA Thiruvananthapuram and BML Munjal University. So may I request you to please come on stage and share your thoughts?
Namaste to everyone. Namaste has an advantage that you don't have to worry about the timing. No, good morning, good afternoon, good evening. Always said namaste. Second is how first has a wonderful meaning. You and I are connected. Just the way that we saw the pedophile. Not we're all not to each other probably. So so that's me without the mask actually. Yeah. It's been 2 years almost, and this was my first conference after 2 years. The last one I attended was in Chennai Mathematical Institute, which Dr. Ajit Kalnikar, Dr. Shovesh Das, they had organized. So it's wonderful to be back in physical form, and we were traveling yesterday from Delhi to Thiruvananthapuram, and that's where BMM Munjal. It's on the outskirts, so Delhi NCR. And we have an enthusiastic team from BMN Munjal. There are 4 mathematicians. I am a non-mathematician, and that's Rubal, who's the head of marketing covering this conference. And she's the mathematician on the making. So we said we force you to attend all the conference lectures so that you become a mathematician at the end of 4 days. So that's BMN Munjal University. It's located at the border of Gurgaon and Rewari in Rajasthan. We have a small 50-acre. And this is where we stay actually. That's the faculty housing or all the hostels, and this is called the Gateway Building. So as you all know, that it's actually a Hero Group initiative. Dr. Rich Mohandan Munjal, who was the founder of the Hero Group, and of course the Hero Group is well known for cycles, electric vehicles, rocket industries, and other things. So we have a thing of 50 acres. Students coming from all the 26 states and union territories. We have a lot of international collaboration. And this was brought up with the vision of, which was very carefully thought that we have to nurture ethical leaders who are skilled, knowledgeable, and have the life skills required for the thing. And we're lucky to have the School of Management, School of Law, and School of Engineering and Technology all under the same umbrella. We are a very young university, about 7 years old. But we already have a few milestones. And in fact, this university was dedicated to the nation by the former President Sri Pranab Mukherjee. At the forefront of the leading change of global education, we trying to contribute to nation building through human resource development, provide access to affordable and high quality education, accelerate research and development, and serve as a role model for higher education, innovation, and best practices. So in BMU, we give a lot of emphasis to the industry collaboration, research, and of course, R&D partnership. We stress that the students, have sort of an experiential learning, which means they have hands-on learning. So at least 30 to 40% of their courses are all connected to, experiential learning in the labs. So instead of having classrooms lecturing, we actually taking them to the industry labs and practice schools. And we have a lot of academic collaborations, which I won't go through. This is the School of Engineering and Technology. We are about 40 members at present. The computer science engineering, mechanical engineering, electronics and computer engineering, applied mathematics and sciences. And that's where the 4 members from BMU mathematicians are from. We also have liberal arts, language and communication and making. So soon we'll have a School of Liberal Arts as well. These have been the thrust areas in research, basically AI, ML, natural language processing, cybersecurity, IoT, robotics, VLSI, smart manufacturing, industry 4.0, automation, mechatronics, nanotechnology and material science, computational sciences, geospatial technology, and many more. We have some centers of excellence supported by the industries such as Shell, Intel, Siemens. And we also have a state-of-the-art facility for the Center for Advanced Materials and Devices. So in the whole, we have a very strong research and innovation environment, which is supported by the Atal Community Innovation Center and other institutes of Institute of Innovation and Entrepreneurship as well. We're also part of the Delhi cluster, which drives innovation. So that is all I had to say. We will be looking forward to your participation. We hope you enjoy the conference and much stuff wonderful campus, and we thank the hosts here and at BMU. And I'm glad that everybody has been able to make it physically. So an enjoyable conference to all of you. Thank you, and namaskar once again.
Thank you so much, sir. It is now indeed my honor and pleasure to invite our Honorable Director to come on stage, Professor J.N. Murthy. Professor J.N. Murthy is the Director of IISER TVM on deputation from the Indian Institute of Technology, IIT Kanpur, and a professor in chemistry, a well-known and renowned scientist of our country. So may I please request you to come on stage and welcome the audience and declare the conference open.
Let me be comfortable for a while. Well, distinguished mathematicians, scientists, postdocs, students of BRICS nations, very delightful morning, a great day. It's indeed a wonderful day, a day much awaited for the practitioners of mathematics of developing countries to come together for mutual learning, exchange, and enrichment in our beautiful campus, IISER Thiruvananthapuram. On behalf of IISER TVM and that of my own, I extend a very heartfelt, warm welcome to all of you. Well, the Foundation Conference was in fact due sometime during July. I believe it was 5th that it was supposed to happen. And this, as I think Professor Meena Mahajan talked about it, this was brought up to me all of a sudden. And she said, would you be interested in hosting this particular conference? It's not that IISER TVM has not had international conferences. I took over as the director of this institution about 2.5 years back. In fact, in about a few months, I'll be completing 3 years here. That was not even 9 months or so. And of course, I had completely taken stock of the institution. And we were having a lot of conferences, but none any in mathematics. I was really keen to have a great conference in our campus in mathematics itself. At that juncture, when she proposed that could we have this particular conference, I really jumped on it. I was really excited. I very much wanted to see the great mathematicians and fantastic practitioners of mathematicians in the country to assemble here. Unfortunately, all that excitement was punctured. We all know the reason, because of the pandemic, which preempted our excitement. Well, we thought we could at least do it sometime during December, by which time we all expected that the pandemic would recede. And we would possibly have this conference happen here. And we know it was not to be. So even that happiness was punctured. And it had to be done someday. And we wanted to do it. Of course, these days, engaging in virtual platform has become an order of the day. If meeting personally, physically is not going to be viable, and you've all gotten used to getting on virtual platform. Well, if it's not going to happen physically, we'll run it virtually, was the decision. And I must tell all the people, particularly the scientists spread across the globe in the 5 nations, even amidst adversity, so much around, everywhere at least the pandemic subsided, but not in Kerala. It's unrelenting in this part of Kerala. Yet, we take pride in saying that our operations in the campus have never halted. Even at a time when most colleges and universities across the country were completely shut down, even today, I would say, with all the Omicron scare, we do have about 1,300 students on campus. At any given time, I think our campus has been more than about 50% in capacity and physical presence. Even for the undergraduate programs where people resorted to all kinds of virtual engagement, virtual learning, and I'm proud to say that we brought the students to the campus. We don't believe in that virtual learning, particularly what demands a hands-on experience. We brought the students here to the campus and have completed all the laboratory courses. So it is with that basis, I pumped up my colleagues, guys, go after, get all your mathematicians to our campus and convince the people. And in fact, Professor Arora of BML Munjal University and I gave a target of about 100 people minimum to engage in this, hybrid mode. I'm sure this really brought a lot of pressure on Professor Vijay Thomas, the head of the department. In fact, even Professor Meena Mahajan herself. I must say, I think her enthusiasm has been really undiminished right from the day that she proposed to me as to whether we could have it on our campus till today. In fact, she arrived 2 days ahead to take stock of things here. But of course, my target was not met. Well, I could have settled with the target of 100, but at least I'm gratified today to see we have about 50 people coming from different parts, with the Omicron scare really coming into the picture till the last minute. But yet, I think we have succeeded to have this really happening in our campus, of course, with all the protocols really followed. It's a great day indeed. In fact, I'm really glad to see we have had in chemistry conference about 200 people. The seminars engaged outside in open air, but probably this is the first conference in-house. I think we did have one in biology, of course, but there was a brief talk or lecture. But really a conference in true sense that stretches for about 3 to 4 days happening under the roof in 3 different, parallel rooms is probably the first time after the pandemic. I think I owe a lot to my colleague, the head of the department, Professor Vijay Thomas, and his team and his colleagues from School of Mathematics, and of course the person behind the persons behind the BRICS team, and in particular Professor Meena Mahajan. That said, I think I should talk about my institution. I should resort to a bit of advertisement. I do come prepared, but when I start talking, I think it goes for a toss. I don't know where I start and where I end, but let me see. I think ICTBM is a campus that was founded in about 2008, so which means we are close to about 14 years in existence. And an institution, in simple terms, going by the Ministry of Education of India, Government of India, an institution should be built in about 10 years, but for some reasons, and I'm sure you all appreciate, this is not the landscape that we exist in. The IISc Tirunelveli exists in, I think, the girl student there talked about IISc Tirunelveli. I'd say it's a really beautiful, lovely, small structure that exists in the lap of nature at the feet of Western gods. We've heard about the natural beauty that sort of surrounds us. We exist here, and creating it was really a forest to bring up the structure that you see today as a lovely campus. It wasn't easy. Not surprisingly, it has taken well over 12 to 13 years. We are still in the process of basically combing area to area, and we are striving hard to make it an institution that is unrivaled in the country. And I have a strong team of faculty. I'm proud to say that. I think they are with me, and I'm sure in the years to come, this will be talked about as an institution par excellence and an unequaled in the country. And it is with that mission we are working here. As for the programs are concerned, right, we only have about 5 disciplines. In fact, the 5th discipline was only started last year, the data sciences, right? So we have physics, School of Physics, School of Chemistry, School of Mathematics, School of Biology, and data science. Data science is yet to take off. So we are supposed to have a faculty strength of about 100, and which is going to sort of expand into about 140 pretty soon. But as of now, we have about 80 faculty. and close to about 350 PhD students. And the most important program here is the BSMS. This is for the benefit of the mathematicians abroad who are possibly listening to us or attending this inaugural conference to tell you about what this ISSRO is and what it stands for in the country. It's only one of the 7 institutions in the country. We have what are called as basically BSMS 5-year programs, 5-year program, and a 7-year integrated PhD program for which the students join at the end of bachelor's degree. But for 5-year BSMS program, the students are admitted at the age of 18 years. And our structure is fantastic. The first 2 years, we speak of them as a foundation courses where the students learn everything about physics, chemistry, mathematics, and biology. And in the next subsequent years, they go on to learn something about the professional courses that they pursue, like mathematics, chemistry, physics, or the biological sciences. And the 5th year is meant to provide the students that are admitted with a unique experience, which is where the ISELs are different. ISELs give not only the education, but an immersive research training. So 1 year, the project that they go into the laboratory, in fact, emerge supposedly as well-rounded graduates to sort of plunge into the research moment they're out of here. And that is what the ISELs are meant for. But right now, as I said, we also launched last year a 2-year master's program. And in fact, launched this year, the first batch is in. Our strength is about right now, it is about 1,600 students. And the projection is about in about 3 to 4 years, we'll be overshooting 2,000 on campus. In terms of the faculty, we are looking at about 125, which means about 40 positions or so will be added in the next 2 to 3 years. Right? Yes, we are on an expansion drive. I think I should talk about this being a mathematics conference. I should talk about mathematics. And if I talk about mathematics, I think we have 16 faculty in School of Mathematics. I think practicing, let me see if I understand mathematics. I think algebra, number theory, geometry, I think. And we have topology and the areas that are represented. Unfortunately, we do not have anybody in, of course, there is an analysis, and we do not have anybody in statistics and probability. And of course, we are desperately looking for people in data sciences. I think we are looking at expanding this department to a total of about 25 faculty members in years to come. So, which means in about 2 to 3 years, we will be looking to add about 8 to 9 mathematicians to the School of Mathematics. I think I've given you enough about the School of Mathematics and School of, the institution as a whole, right? Let me see. I think I can go on probably talking about the other disciplines in the campus, and I would not like to do that. I think time is a very precious factor. I think I should say, I should acknowledge the contributions of, as I already said, to Sylvia Thomas, and the key person who Meena Mahajan has been a kingpin in sort of maneuvering the whole thing. And I'm sure we are set for the 4 days proceedings and virtual space as well as in physical way. I'm sure there's a lot to learn for all of you. I sincerely hope that the 4-day proceedings will be absolutely beneficial and highly enriching to all of you, the mathematics fraternity. I wish the proceedings a great success, and with that, I declare the BRICS conference, the 4th version, open. Thank you very much.
Thank you so much, sir. So with that, I think I can say now that the day 1 of the conference has begun. Our very first talk is a plenary talk by Professor Meena Mahajan, and the session will be chaired by Professor R. Balasubramaniam. I would like to request all the online participants to kindly send in their messages with their doubts or comments or at the chat section on the Zoom meeting. And with that, I'd like to transfer the virtual mic to Professor R. Balasubramaniam. Thank you, everyone.
Thank you. Is it time to start?
Yes, sir.
Okay. Is Meena around?
Yeah.
Meena?
Yes, I am here.
Ah, fine. Okay. Let me welcome all of you for this very first session, which will be given by Professor Meena Mahajan on short proofs and the non-existence of short proofs. And she has been my colleague for the last maybe 15 years. And we were together in IMSc, and she continues to be in IMSc, even though I have come out of IMSc. And yeah, let me just invite her. Can you share your screen? Meena, yeah. Yeah, please go ahead.
Hello, everybody. I hope I am clearly audible now.
Yeah, you are.
Okay, thank you. Yeah. So to begin with, let me first thank the organizers for inviting me to give this talk here at the BRICS Math Conference. I'm not a mathematician, I'm a computer scientist, but within computer science, I do theory, and theoretical computer science is very closely linked to mathematics. It uses a lot of, it learns a lot from mathematics, and sometimes it also gives back to mathematics in some ways. So in this talk today, I want to talk about a problem area that I've been working on in the last 10 to 12 years, the complexity of formal proofs. So let me spend some time trying to explain the setting. What exactly is this, are we talking about when we say formal proofs? So by way of example, consider, I see the slide is not changing. Yeah. How do we state proofs? This is the important thing that we want to address. So consider this here. There are infinitely many primes. This is something that we all know. And let's say you are asked to prove this. Well, the first response might well be that, this is completely elementary. I mean, here we are in a math conference, and why should this need a proof? But depending on whom you are addressing, you perhaps, it's a high school student who has not really thought much about this. And then you could give a nudge and say, look, this is how you could prove this. And that would probably be fine. But maybe the student has not even at high school, maybe is in 9th or 10th standard and needs a little bit more convincing. Why is even this number written out there not a prime? So then maybe you will give some more details. So you see these three proofs up here, proof 1, proof 2, proof 3, depending on who is reading it, they would all be acceptable in some settings and not acceptable in some other settings. And what we are going to talk about today are not these kind of proofs. We are going to talk about formal proofs. So it's important to make the distinction, what changes between these proofs and those proofs. So what we can take away from that previous slide is, what is the reason why there are such different proofs? It's because the goal of a proof is really to convince the target audience. The target audience is the reader, or in this case, the listener, or somebody who's verifying the proof. The goal is to prove that to that person, convince that person that the claimed statement is correct. And there should be enough detail so that this is convincing. There's also a second reason, which I've written out here, which would be the goal is to convince the person who is reading it that the person who's writing the proof really knows the proof. And this kind of a goal is what comes up when we are talking about writing a proof in an exam or in an assignment. It's not that the teacher does not know the proof. So you don't want to convince the teacher that the statement is true. You want to convince the teacher that you know. So this second goal is not what we're going to address today. We're looking at the first goal. There is a claimed statement, and the prover wants to convince the verifier that this claimed statement is indeed a valid statement. So what's going to affect the level of detail required? Clearly, it's going to depend on the ability of the person who's reading the proof checker. Since we are looking at only the first goal, what exactly do I mean by ability? Well, for one, mathematical maturity. That was the main difference between those proofs 1, 2, 3 that I showed right in the beginning. The facts that are already known to the checker. So if you know that the checker knows certain theorems, then you could use them for free in your proof. But if the checker doesn't, then you will have to substantiate that. And even with sufficient mathematical maturity and sufficiently large knowledge base as represented by these facts which are already known, it could be that the checker simply does not have enough time. So you would like the proof to be perhaps short and compact with all the necessary information, but not too long. So these three things are going to affect what would be considered a reasonable proof by the person who is reading it. Now, modern proofs are increasingly being checked not by persons, but they are being checked by programs. Some proofs are even produced, not just checked, but some proofs are even produced by programs, and whether this is good or dicey is a completely different discussion. lot of discussion I have seen on math fora in particular about, is this really math? In fact, we will come to that point a little later as well. But right now I am focusing on the first part, checking a proof by a program, not so much producing a proof, but checking a proof. Okay. Now programs, even if they are written by coders who have immense mathematical maturity, they have a large knowledge base, they have lots of time, the three things which I said affect the ability of a checker. So even if the coders who are writing the program are whales in this, the program is after all an inanimate object which follows the rules. And therefore a program is going to expect that the proof adheres to a very rigidly specified syntax, and it uses inference rules which are specified in a completely unambiguous way. And this is what really builds up the definition that I'm talking about, a formal proof. So what do I mean by a proof system? Proof system is the system in which we are going to represent formal proofs. So by a proof system, what I mean is the following. We fix some class of theorems. We cannot have a proof system which caters to all theorems in the world. We have to fix the class of interest. We fix an alphabet of sigma of some letters which we will use for representing the proofs. And then the proof system is, for a proof system for this class, is basically a map which takes words over this alphabet, maps them to some other words. The idea being that the proof system is taking an input word and interpreting it as the proof of some theorem. And then it's going to try and check, is this proof indeed a valid proof? If it is a valid proof, it should output the theorem. If the proof is not valid, then it will not output that theorem. It will throw away this proof and maybe output just some default theorem. Okay? So the proof system is a map which maps words to words, and it satisfies two conditions. The first condition is soundness. No matter what input word is given to the proof system, the output that it produces is always a theorem from the class C. The range of this map P is completely contained in C. So it means that P is proving theorems only in C and not anywhere else. No other theorems are provable by this system. So we're talking about a proof system for the class. So this is the soundness condition. Okay. So there's also the completeness condition. The completeness condition says that for every theorem in this class, there is indeed a proof, which this proof system will produce. For every theorem in the class, there is a proof, there is a word pi, such that when the proof system is given pi, it produces the theorem P, which means that the proof system considers pi a valid proof of T. Okay. So this is saying that the range of P contains all of C. All theorems in C are indeed provable in this proof system. Then this proof system is complete for the class. So these are two notions which are very obvious. You would demand them from any reasonable proof system, and they come from the setting of logic. What comes from the computer science and complexity viewpoint is this third condition, which is efficient checkability. So a proof system is a map from words to words. This map should be efficiently computable. It's not enough for me to see that there exists a map. I want to know that I can compute this map efficiently. Verifying a purported proof of some theorem should be possible efficiently, which means that there is an algorithm which computes the theorem extracted from the proof pi in time, which is, this is now the go-to default definition of efficient in computer science, polynomial time. So the time required to extract the theorem is polynomial in the size of the proof. Whether polynomial is the right definition or no is again a separate discussion. It's largely accepted by our community that polynomials are good and super polynomial time is too bad. So we are going to stick to this definition. So this definition of a proof system was originally formulated by Stephen Cook and his student Rekau way back in 1979. And since then we have come a long way, depending on your point of view. Let's see, what is the biggest question that could be posed here that was posed by Cook and Rekau themselves? Which are the interesting theorem classes C, which have proof systems P, where every theorem has short proofs? Now, every theorem having short proofs is not linked to efficient checkability, because checkability says that, okay, the proof should be checked in polynomial time, but the time is polynomial in the length of the proof, not in the length of the theorem. So it could be that the proof is huge, but compared to the size of the proof, the time to check it is reasonable. But the proof is really huge compared to the theorem statement itself. Now, this does not make sense if we are thinking about a theorem as one single statement. it's a constant size object. So what do we mean that the proof is large compared to the size of the theorem? This needs some formalizing, some setting up, and I will come to that very shortly. Before that, let me say a little bit more about this question. Okay? So we're talking about proof systems where every theorem has short proofs. What is known is that this class of theorems belonging to the family propositional satisfiability is a propositional formula satisfiable. This class has short, easily checkable proofs. And let me throw a few buzzwords for those who do know these terms in computer science. It will just give you some context. If you don't know it, it's perfectly fine. It's not necessary for what follows. So propositional satisfiability is the canonical NP-complete problem solvable in non-deterministic polynomial time. And therefore, every problem in NP corresponds to a class of theorems for which we indeed do have such proof systems. So a proof system is also, it's giving you a format in which to write the proof. And there are proof systems where the proofs are short. What is not known is whether propositional tautologies have short proof systems with short proofs. So satisfiability is saying there is some way of making this formula true. Tautologies are saying that no matter what values you give to the variables, the formula ends up being true. And this corresponds to the question of whether NP and co-NP are the same or no. And that is where Cook and Rekau came to this problem. This is a slightly easier question which one could pose, because here we're asking, which classes have some proof system at all. What we could do is we could fix specific proof systems in our approach to trying to understand what all possible proof systems could do, fix specific proof systems and ask, okay, if I fix this system P, in this, is there a theorem which is provable in the system but is not provable by short proofs? And this question we have made a lot of progress about in the last 30, 40 years. So as a concrete example, because I said, a theorem you think of as a constant size object, what do we mean by short proofs? So we're going to say that a class has short proofs, and again, short means polynomially bounded for us. So a class C has short proofs in the proof system P. If there is some polynomial, and for every theorem T in that class, there is some proof, alleged proof word pi, such that the proof system maps pi to T, and the length of pi is this polynomial P in the length of T. So I'm using this notation to mean the length of the proof or the length of the theorem. So for this, we need theorems which are growing in length. So for instance, the first theorem which I said, there are infinitely many primes, maybe we should consider instead a parameterized theorem class from here. Tn is the theorem that says that there are more than n primes. And pi n is a proof of Tn. It's not a proof of the original theorem T, it's just a proof of the nth theorem in this class. And now one could ask, how does the proof of pi n grow as n grows? So one could think that the original proof we had, it applied for all n you fix arbitrarily. So it really, the proof length does not depend on n. It's one proof which works for all n. But that's misleading. The proof does depend on n in the sense that inside the proof you are writing n somewhere. And so at least the representation length of n figures somewhere in the proof. Well, maybe this is too contrived an example. Here's another concrete example. Consider the following statement, the statement Sn. So I'm looking at a family of statements indexed by n. The nth statement says that the set of first n natural numbers can be partitioned into two sets. And within any one set, there is no Pythagorean triple. Pythagorean triple is just a triple ABC such that a square plus b square is c square. So I take the first n numbers and I can partition them into two parts, such that every Pythagorean triple is broken by this partition. One number is here and the other, but the numbers get split across the two sets. And the conjunction of all these statements would say that the set of all natural numbers can be partitioned into two sets, neither of which contains a Pythagorean triple. So this is the Boolean Pythagorean triples problem, deciding whether S is true or false. Some of you probably know a proof of this, some of you don't. It's very interesting to think about how one would even go around proving a statement like this. So one thing to note is that, of course, if S is true, then every Sn is true. You can partition all the natural numbers. Of course, you can partition a subset as well, breaking the triples. So if I want to disprove S, it would be enough to disprove any one Sn. If I want to prove S, then I may be better off not tying myself down to a specific n. How are we going to prove or disprove any Sn? Well, this problem was solved in 2016 by 3 computer scientists, Euler, Kuhlmann, and Marek. And they solved it by using the following approach. They wrote the statement Sn, which is talking about a particular finite subset of n, in a suitably chosen logical language. The logical language they chose was propositional satisfiability, which, as I mentioned earlier, was the canonical NP-complete problem. And then they used computer-assisted proof search to find or to rule out a proof of Sn. And this proof search was in a specific proof system. The proof system is loosely based on a system called resolution, which I will shortly describe, but it's not exactly resolution. So in that sense, this is a computer-assisted proof search. I did say in the beginning, they're talking about proof checking, not proof search. The interesting thing is that they used computers for the proof search, but they also used it to check their own. And so in that sense, this particular proof of this theorem is different from previous computer-assisted proofs of famous mathematical theorems, like the four-color theorem immediately jumps to mind, or the resolution of the Kepler's conjecture. The computer was used in a certain way to come up with a proof. Here also the computer was used to come up with the proof, but it was also used to certify the proof. Maybe it's a cyclic argument. If you don't trust the computer to come up with the proof, you won't trust the certification. But it depends on what the certification is. So let's see a little bit more about this. Well, a more practical setting for checking proofs is that of formal verification of systems or programs. Does a system always behave as expected? Does it behave as expected on long enough runs, if not always? So the requirements of a system, so the system could be the system underlying a chemical plant process or a medical system or whatever. So it could even be an ATM or a coffee vending machine. Does it behave as it is expected to when it interacts with its environment? So you formulate all the requirements as logical statements, and then the system is good if for all runs, either for all runs or for all runs up to a certain length, it behaves as expected. It is bad if there is some run of the specified length where it violates some constraint, does something that it should not. So now we will, having formulated in this way, we prove that the logical formulation of this statement, the system behavior violates some constraint. This logical formulation we will try to show is simply unsatisfying. There is no way to make the system behave in a bad way. And that would certify that the system is good. So this is the practical reason why we would be interested in formal checking. There's another related big question. So the first thing to note is that if potential proofs of unsatisfiability or satisfiability or of the fact that something is a tautology, if these potential proofs are very long, then an automated proof search will also take too long, clearly, even if you have a very powerful computer. So lower bounds on the proof size in a specific proof system, showing that in this proof system, there is no proof shorter than this. It kind of exposes an inherent limitation of a proof search based method. If you're hoping to search for a proof in an automated way and there is no short proofs, then you are bound to take up. However, it could well be that there are short proofs, but we don't know how to find them. And this again relates to the famed computer science question: is P equal to NP, deterministic versus non-deterministic polynomial time? So maybe there are short proofs, but we don't know how to find them. So that's the next big question. For which interesting proof systems is it the case that whenever short proofs exist, we also know how to efficiently find them? And this is the proof search question, which I am not going to address. Like I said, I am going to restrict myself to proof checking, but I wanted to throw this out here as a very important question in this area. Okay, so like I said, I'm going to talk about proof systems which use propositional and generalizations thereof. So what is this propositional proof system? In the propositional proof system, the format of a theorem is a propositional tautology. So what do I mean by this? There is some expression in these variables x1 to xn. This expression involves Boolean valued variables which take the values 0 or 1 standing for false or true. The variables are connected via Boolean connectives, the logical and, the logical or, logical negation. And the expression is a tautology if no matter what Boolean setting we give to the assignments, the logical expression evaluates to true. And a most trivial example would be the expression x or negation x. No matter what value you assign to x, either x or negation x is true, and therefore this is a tautology. Here's a more non-trivial example. I have a fairly longish formula written here: negation x1 or negation x2 or ... negation xn or yn or x1 or negation y. Well, you can read it here. There are also some more terms here. Okay? And I claim that this is a tautology. Now, this is something which is small enough that I have written it here and you are reading it on the screen. But so conceivably, if I give you 5 minutes to look at it, which I won't, but if I did, you could figure out that this is a tautology. But imagine the computer program which is going to be given things like this with thousands of clauses, thousands of terms. So that's where the need for rigid syntax and inference rules comes in. So well, why is this a tautology? It's best to view these terms pictorially like this. You have this comb-like structure with arrows going up, and the x variables are sitting at the ends of the teeth, the y variables are sitting on the spine. And take any assignment, either it satisfies one of the first two lines itself, that is some x is false or y is true. Or maybe it satisfies the third line, which is essentially saying that x1 and y1 take different values. But if it's not satisfying all of these, then what we know is that all the x's are true. Therefore, y1 is also true. yn is false. So somewhere along the way, there must be some y which is true and the next y is false. And then corresponding to that place, there is a term here which says, the current y is true, the corresponding x is true, but the next y is false. That term will be true. So in any case, some term in this expression will be satisfied. And so this is a tautology. Now, this looks like a really toy example. But if you think of a system which involves thousands of variables, there could be substructures sitting inside which are expressing various logical constructs. And this could be one such construct. So the program has to detect this quickly. How are they going to prove that an expression is a tautology? Where fx is a tautology means that for every x, fx is true, which means that there is no x for which fx is false. There is absolutely no x, no assignment to the x variables which can make the negation of fx true. In other words, the negation of fx is something which is unsatisfiable. So we are going to focus on deciding, is a propositional formula satisfiable or not satisfiable? That's the NP question, or the co-NP question. Satisfiable, NP, unsatisfiable, which is equivalent in some sense to proving that its negation is a tautology. That's the co-NP question. But this is a computationally hard question. Very likely we don't have efficient algorithms for it. The surprising thing is that despite this computational hardness, there are many modern day practical solvers which are used in real world applications, which very efficiently decide whether a given expression is a tautology or no. They're efficient on quite large instances. I have conservatively written here thousands of variables, but even there are some of them which work even on millions of variables and do the job. If f is not a tautology, then the run of this so-called SAT solver, it quickly finds an assignment which makes the negation of fx true. So it proves that f is not a tautology by giving that assignment. If f is indeed a tautology, then also the run has to give a proof. But that proof is implicit in the way the SAT solver proceeded. So from the solver algorithm, we can extract the rules that the solver is using and formulate a proof system. So remember, a proof system is the set of inference rules that we allow, the syntax of the proof and the rules. So we can extract such a proof system from every SAT solver. In particular, that Boolean Pythagorean triple problem. What Euler-Kuhlmann-Marek did was that they used Boolean variables to denote a partition of the natural numbers. In particular, xi is 0, that means I goes in the set A0, xi is 1, it goes into the set A1. And now there are constraints for saying that there is no Pythagorean triple in one part. So if A, B, C form a Pythagorean triple, then they put in these clauses, a disjunction of terms, with saying that at least one of xa, xb, xc must be true. So at least one of them goes in the set x, A1, and at least one of them must be false. xa, xb, xc, at least one of them must be false. So at least one of these three numbers must go into the set A0. So you've broken the triple. So for every Pythagorean triple in the set, you have these clauses. And now the statement essence is that there is some partition for which all these clauses are satisfied. And now you use a SAT solver. This is the part which I am particularly interested in. Not so much the statement that they prove, but the fact that they used a SAT solver to prove it. Satisfiability and propositional proof systems. For n up to 7,824, their solver runs showed that it is satisfiable. So Sn is true, but at 7,825, they showed that it is impossible to do this partitioning. So that statement was false, and therefore S is false. The Boolean Pythagorean triples problem conjecture is known to be false. And to see that, they had to write down all the Pythagorean triples up to 7,825. There were more than 9,000 of those. Each triple only gives rise to 2 clauses. So the formula had roughly 20,000 clauses and roughly 8,000 variables. The solver was able to solve this. It's a large number, no? Especially if you think of a brute force method, which would involve exponential blow-up. 2 raised to 1000 is not something that we want to think about. So obviously they didn't do brute force. There was a smart SAT solver algorithm sitting there. Even that smart solver, it ran for 30,000 hours. So it's no joke. So this 30,000 hour run, finally, it gave a solution. It gave a proof. The solver was loosely based on resolution, but the proof that it is unsatisfiable was in a more involved format, DRAT, which I won't talk about. And the proof length was 200 terabytes. So where is the scope of a human being sitting and checking this proof? They say, okay, we have a computer-assisted proof and nobody's going to believe it. So then they said, we also have a way of letting a computer check that this proof is correct, a different computer program. And that was the proof in the format of DRAT. They also did afterwards compress the proof down from 200 terabytes to 68 gigabytes. I'm not going to read 68 gigabytes either. So as far as I'm concerned, it's too long. This was some of the hype around this thing in 2016. Largest math proof ever, and finally the question, is this really math? So I don't want to address the question, is it really math or no? The question I want to address is, how do you deal with satisfiability? That's a computationally hard problem. All my instinct tells me there should be no efficient algorithms for it, but it looks like in many cases there are. Why do they work? So a specific proof system, resolution, it's a proof system which shows that a formula is a tautology or that its negation is unsatisfiable. It's the most well-studied propositional proof system. It underlies most of the most widely used real-life SAT solvers. What is the syntax? So the format for theorems in this is a set of clauses. And that's why for the Pythagorean triples problem, I showed you what the clauses are. Resolution expects the theorem to be stated like this. So the theorem is saying that there exists an x1, there exists an x2, there exists a y1, y2, and so on, such that all these clauses are satisfied. That's the syntax of a theorem. The there exists part is implicit, so we don't even write it, we just write the clauses. What's the syntax of the proof? So the inference idea is that if I have an assignment which satisfies a whole bunch of clauses, and let's say in that bunch of clauses, I have a clause A or X, and I have a clause B or negation of X. Well, if the assignment satisfies both these clauses, that same assignment must also satisfy A or B. Because X cannot be both true or false. It cannot be that both these clauses are satisfied because of X. So one of these clauses is satisfied independent of X, and then that will allow you to satisfy A or B. So this is one idea. The other idea is that there is no assignment that can satisfy the empty clause. To satisfy a clause, you have to make some variable in that clause true. The empty clause has no variable. So the inference rule in resolution is so simple. It just says that if you already know A or X and B or negation X, you can infer A or B, and you want to try and derive the empty clause, which proves that the formula is unsatisfiable. Maybe an example will make this clearer. There are some clauses which I have shown here boxed in green. These are the clauses which are given to us. And we are trying to prove that it is impossible to simultaneously satisfy them. These are exactly the clauses which were on that comb which I drew earlier. Well, the resolution rule here, I have x1 and I have negation of x1. So I can drop these two and the rest of it is y1. So any assignment which satisfies these two must satisfy y1. Any assignment which satisfies these two must satisfy negation of y1 or y2 because the x2 gets cancelled by resolution. Any assignment satisfying these three must satisfy this. Each step here is an application of the resolution rule. So therefore, any assignment which satisfies all these green clauses must also satisfy all the clauses at the next level. And therefore, it must also satisfy all the clauses here. It must satisfy here. It must satisfy this. And since there is no assignment which can satisfy this empty clause, therefore, there is no assignment which satisfies all the green clauses. This is how a typical resolution proof works. And there are many things that resolution can do very easily. Okay, now think of resolution as a proof system. It's given the sequence. Pi is a sequence of steps where you're applying resolution to clauses and finally it produces the empty clause. So it's very easy in resolution to prove this. I had this comb-like structure where at all the source, it was a directed acyclic graph. At each source node, you have a true value. At the final sink, you have a false value, and you have clauses which say, look, if all the incoming values into a node are true, then the variable at that node must also be true. So truths must be propagated up, but finally you must get false. This is obviously unsatisfiable, and resolution can very easily demonstrate that this is unsatisfiable. Not just for the comb structure, but for any directed acyclic graph. But there are many other things that resolution cannot do. For instance, the mutilated chessboard problem. You take a 2n by 2n chessboard, knock off the opposite corners, and then say, I can cover this with 2 by 1 tiles. Obviously, you can't do it. You can formulate this using logical clauses, and resolution get stuck. Well, it can prove it. Resolution is a complete proof system, but it takes humongously long. The pigeonhole principle, startlingly even more simple. N+1 pigeons cannot be assigned to n holes without collisions. I mean, this is like being brain dead. No, obviously this is true. What is there to prove about? Now, the point I'm making is that this construct could arise again when you're trying to verify formally some system. You have a system with millions of variables in some chemical plant, and you're writing the conditions for safety, for whatever, and maybe somewhere in that there is this thing that there are no collisions. So it's not told yet. It's not told to you explicitly that this is an instance of the pigeonhole principle. It is sitting there encoded, and the program has to detect it and then quickly work out. Well, what I'm saying here is that even if it is detected that here is an instance of PHP, of pigeonhole principle, there are no short proofs in resolution. Similarly, there is the click co-coloring problem. A graph cannot have a k click and a k-1 coloring. This is also something which is, for those who know the graph theory notation, this is very obviously true, but resolution struggles to prove this. In case I have lost some of you in the sense, what exactly do I mean by proving pigeonhole principle? Let me very briefly tell you what I mean by the formulation. Okay? So the pigeonhole principle is saying that n+1 pigeons cannot be assigned to n holes. To formulate this in the syntax that we have agreed resolution will use, we use the Boolean variables xij. I is the ith pigeon, j is the jth hole, xij is 1 means the ith pigeon goes into the jth hole. And then I have clauses, which are my constraints in the expression. The clauses, for each pigeon, I have a clause xi1 or xi2 or xi3 or xin, up to xin. The ith pigeon goes somewhere. It's not left homeless. And for distinct pigeons, I prime, and for a whole j, we have the clause which says that either pigeon I is not going into whole j or pigeon I prime is not going into whole j. Both of them are not going there. Okay. So if you collect all such clauses, and all such clauses, you are expressing the pigeonhole principle. It has roughly n square variables, n into n+1. It has roughly n cubed clauses, and resolution can show that it is unsatisfiable, but any proof, it has been known since 1985 or so that any proof in resolution must require 2 raised to omega n length. So this, to me, encapsulates what I said when I started out, that here is a formal proof system in which the syntax is rigidly specified, inference rules are unambiguously described. Here is a tautology. This proof system has no short proofs for this tautology. It does have a proof, but it does not have a short proof. Now, I hope I have a few more minutes. I would like to go a little bit beyond SAT and talk about what is more exciting to me, because this is what I've been working about in the last 10 years or so. Beyond SAT, inspired by the success of resolution-based SAT solving, people are aiming for proof systems which handle more complex formulas. So a propositional tautology, remember, it looks like this. You have some expression, and then you have these for all quantifiers. For every value to the x's, the formula f is true. The way I'm going to add complexity is by mixing the for all and the there exists. So for instance, there exists an x1 to xn such that for every y1 to yn, the inner product of x or y, written like this, is an even number. This is clearly true. Take x to be 0, then the inner product is 0, which is even. There exists an x such that for every y, the inner product xy is odd. This is false, because if y is 0, then the inner product is not going to be odd. For every x, there is a y such that either x is 0 or the inner product is odd. Well, this is true. It requires just a little bit of thinking. X has at least 1, and you can pick it up. So now you see these statements, they're using existential quantifiers and universal quantifiers. So the whole complexity of proving that the statement is true or not true is going to change dramatically. And indeed, these are no longer NP or co-NP problems. These are what we call p-space complete problems. They are not more expressive than tautologies. Whatever you can say with a tautology, with these kind of expressions, you can say with the ordinary tautologies also. But they can express many theorems much more succinctly. The length of the theorem itself becomes shorter. And remember, our measure of the length of a proof is related to the length of the theorem. So now, let's say I had a theorem this big and I had a proof this big, and I said, well, the proof is reasonable compared to the theorem. But now suddenly I've changed the language of the theorem. The theorem is so short, the proof is still so long, it's too long. So with this new language for theorems, now we ask which kind of theorems have short proofs. And these are what are called quantified Boolean formulas. Every variable is quantified in a particular way, either existentially or universally. The quintessential quantified Boolean formula problem is the last letter game, which I'm sure Almost everybody here in this audience has played at some point or the other. You fix a set of words, player one picks some word, then the next player has to pick a word which begins with the last letter of the previous word. And you keep going. You're not allowed to repeat a word. Whoever first cannot play loses. When on songs, if the set of words that you fix is songs, then this is the game Antakshari, immensely popular all over India. If you fix place names, this is geography, film names, whatever. The question we are asking now is, in this game, is it the case that the player who starts has an advantage and can always win? Does player one have a winning strategy? No matter how player two responds, player one is able to respond in such a way that it drives the game to a win. So the abstract representation for this would be, you have an inner propositional formula. Typically, I will assume that it's a conjunction of clauses, though it's not necessary to be so. I have Boolean variables. These Boolean variables are encoding the moves. So, for instance, I could say there exists a move of player one such that for every move of player two, there exists a move of player one such that for every move of player two, and so on, over n moves, because the given dictionary of words has n missing, such that when they play according to this, at the end, player two is stuck. So these Q1, X1, Q2, X2, these Qs are quantifiers, exists or for all. And this very naturally encodes not just the last letter game, but in general, any two-player game of this form. So the existential player owns all the variables which are marked existential. The universal player owns all the universal variables. And then the game is that they go through this list in that order. No, the game move 1, move 2, move 3, move 4. So in that order, they have to choose the values to their variables. By the time they reach this point, all the variables have values. Now you plug in those values here and check whether F is true or not. A QBF is true if and only if the existential player can win. So here's a concrete example. A formula, there exists x1 to xn. For every u1 to un, there exists t1 to tn, such that all these clauses are satisfied. Requires some thinking through, is this true or is this false? So let's try out some games on this. On EQ3, let's say the first player says, I choose 001, player 2 says, I choose 011, then for use, then player 1 responds with these are the values for t, and now all the clauses are satisfied, existential player wins. Another run, the player again says 001, this time the universal player is smarter and says I choose 001, and player 1 thinks a lot, does this, but still, one clause is falsified. Universal player wins. It turns out that in this example, the universal player can always win by just setting each UI to be equal to the corresponding xi. So the universal player has a winning strategy. This winning strategy is unique. Now let's look at how are we going to prove QBF's false? Well, one way would be to say, show that the universal player has a winning strategy. But how do you even describe that strategy? So more generally, a proof that a QBF is false, well, if all the quantifiers are universal, then a falseness proof would be just one assignment. That's an NP type of proof. If all the quantifiers are existential, then it could be a resolution proof. That's a co-NP kind of proof, tautologies. But when you have mixed quantifiers, that's where the game changes. And the resolution rule still remains sound, but it's no longer complete. So you need some other inference ideas in addition to resolution. And there are different flavors of new ideas that could be used. One idea is the universal reduction rule. Let's say I have a QBF which is true. True means that the existential player has a winning strategy. Somewhere in that expression F, there is a clause C or U, in which U is some variable here in the prefix, and all the remaining variables in C come before U. Then you imagine the game being played. The existential player can win. By the time it is the turn of the universal player to fix the value of U, that clause C had better already be satisfied. If all the variables of C have been set and C is not yet satisfied, the universal player is going to say, aha, I got you, I'm going to set you to make this false. So if indeed existential player has winning strategy, it has to satisfy C also. So throwing in C into the expression along with F preserves truth. So this is the universal reduction idea. You use resolution, you use reduction, that is you add more and more clauses obtained by killing of these universal variables. And again, you try to derive the empty clause. That's one way of proceeding. Another way of proceeding would be to simply use the meaning of universal for all quantifier. For all U, there should have been, for all U, some expression inside means F0 and F1, right? So you judiciously try to expand the formula, you use clever extensions, combinations, so on. And you have a proof system. The rules are very rigidly specified. You can use, for instance, in this first case, you can use resolution and you can use this reduction, change C or E to C. But why are these proof systems at all? So remember, a proof system had three conditions: soundness, completeness, and checkability. Efficient checkability is like a given the way the rules are specified. Completeness is usually easy. You assume that the formula is false and there is a winning strategy for the universal player, and you can use that strategy to construct a proof in this format. Soundness is usually more involved. What it involves is saying that, from an alleged proof that the statement is false, somehow extract a winning strategy for the universal player, for all players. And once you can show that that strategy which you have extracted is winning, then you have shown that the formula is false. So this extraction is not always easy, but at least usually it is constructive. So that's good news. So how would you prove that some statements are hard to prove in such a proof system? Remember, our focus is when are there no short proofs? So there are two approaches. One is semantic cost. This is the cost of a formula itself, nothing to do with which proof system you're using. So if a formula is such that for all universal variables, you need lots of values to completely specify a winning strategy. For instance, in this example, you need all the 2 raised to n settings to the u to be able to completely describe a way in which this player can always win. Well, then this formula has high semantic cost. And in many proof systems, high semantic cost means there is no shortcut. Technically proving this does require a lot of work, but this is the idea. There is an intrinsic measure of complexity of the formula. If that measure is large, then there is no shortcut. There is also computational hardness. So if a formula is false, then we know it means that the universal player, the for all player, has a winning strategy. So what does a winning strategy mean? That, if you tell me what the other player has played till now, I'll tell you what is the next move to make. So you can think of this as a computational task, right? I mean, Vishwanathan Anand sitting playing a chess game, he has to compute what is the next move that I should make based on the past history. So this strategy has to be computed. If this strategy itself is hard to compute in some appropriate model, in some appropriate computational model related to the proof system, then a large proof size will be necessary in that proof system. For example, if you look at this formula, which is I call it the parity formula. It says there exists an x, a vector of x variables, such that no matter what value you choose, for u is not equal to tn, but the other constraints essentially say that tn is the parity of x. If x is odd, then tn is true, otherwise tn is false. So it cannot be that no matter what value of u you choose, tn is not equal to u. And there is a unique way for the universal player to win, which is to set u to be equal to the parity. Then either this last constraint will be violated or something here will be violated. But it turns out that computationally, parity is a hard problem. I mean, we think of it as a very easy problem. You have just n bits and you just want to know odd or even. But there are restricted computational models, decisionless, constant depth circuits, where probably we know, and we know this since the 1980s, that you need exponential size. So proof systems for which when you extract the strategy, you're going to get a computation of the strategy in this model, they will require large proofs for this model. So these are some ways in which one could prove that QBF proof systems also require large proofs for certain formulas. Just a couple of minutes, I want to talk about a new QBF proof system. I want to mention this. This is some work that I did recently with my these are my collaborators. So Olaf Beiersdorf in Germany, he is in fact, I think currently the world leader in QBF proof complexity. And I learned QBF proof complexity from him in the last 10-12 years. Joshua Blinkhorn was his PhD student, Gaurav Sood is my PhD student, and Tomasz is a postdoc in Olaf's group. And what we did was to try and understand this hardness that comes into QBF proof systems. How can we avoid this hardness and get short proofs for more QBFs? We proposed a new format. And in this new format, the winning strategies don't have to be extracted from a proof. They are actually written in the syntax of the proof. So we completely changed the syntax of what goes into a line of the proof. We encoded partial winning strategies in the lines. As a result, soundness became completely trivial to prove. Completeness also was easy to prove. And for some cases, for some formulas, for instance, the equality formula, the parity formula on the previous slide, this system overcame both those bottlenecks. There were formulas with high semantic cost, but they had short proofs here. There were formulas which had a high computational hardness like parity and inner product, and they have short proofs here. And so there were a lot of technicalities involved in the setting up of this proof system, and I will not spend more time on that. But I just want to say that thinking through these ideas, what goes into the inference rule and where the hardness comes from, can lead to these kind of new insights. And maybe these could be used to design newer solvers, newer proof systems and newer solvers. Unfortunately, we also showed that a completely different QBF family, which does not have semantic hardness, it does not have computational hardness, the winning strategy is trivial and the semantic cost is low, and that turned out to be hard in this proof system. So basically the take home message was that it's all horribly mixed up. So each proof system has its own strengths, some formulas it can prove easily, and it has some limitations. Some formulas it simply cannot do. So will this new system merges, will it be useful in practice? Well, the jury is still out. Is it interesting in theory? Emphatically, I would say the answer is yes, because it's showing that both hardness sources can be simultaneously tackled. So as a practitioner who's designing solvers, there is an interesting message here to be taken away. Okay, so now I think I've reached the end of my time. I had 2-3 slides describing very briefly the idea behind this proof system, but I'm going to skip them because they are not so important. Let me just go to this final take-home message. So what I have talked about is the complexity of formal proofs. How complex does a proof need to be? Well, it depends on the choice of language in which you represent a theorem. For instance, tautologies versus QBFs. The theorem becomes shorter, then the proof size could become larger. It depends on the syntax of the proof. How do you specify each line of the proof? It depends on the choice of the inference rules. How much are you allowed to take for free and say from one step I can go to this next step in next line in a single step. So the proof complexity depends on all of these. Once you specify them explicitly, proof complexity is aiming to understand the limitations of seemingly successful solvers by explaining the underlying proof system. It's hoping to separate and collapse complexity classes that also based on proof lengths. I mean, I would love proof that NP is not equal to co-NP based on proof complexity, but for that matter, I do not even know that NP is not equal to co-NP. Maybe they are equal, and even that would be immensely interesting, both computationally as well as from a proof complexity viewpoint. SAT solvers are useful in proving mathematical theorems such as the Boolean Pythagorean triple problem. SAT solvers were a tool used. It was not a special purpose tool designed to solve that theorem. SAT solvers, the SAT solvers they used have been used in many other contexts. They were used in this context to prove this theorem. They are useful to prove the theorems. They are useful to ratify the proofs of the theorems. And propositional proof systems are explaining the underpinnings. But QBF solvers are going much beyond SAT solvers. They are handling much more complex theorem statements. They could be much more useful in formal system verification, where very naturally the constraints that we want to specify involve mixed quantifiers. There exists and for all. They are not of just one type of quantifier. So this QBF proof complexity is a relatively younger field. It's taking off now, and an invitation.
Meena, this is your last slide?
Yes, this is my last slide, and this is my last line, an invitation to join the QBF proof complexity endeavor.
Yes.
Yes. So thank you very much, and I'll be happy to take questions now or also later in any discussion forum. Thank you.
Good. Yeah, it was a very beautiful lecture, and in fact, what we mathematicians do is more or less a table talk on whether the computer aided proofs are really proofs at all. But then you say that this question has more intricacies and more subtleties involved what the computer can solve and not solve. And since we are little running out of time, probably 1 or 2 questions might be okay. And anybody who wants to either raise your hand or unmute and then please ask. Okay, if there are no more questions, let's thank the lecturer for such a beautiful talk.
Thank you very much.
Yeah, and I go back to the organizers. Okay, let the organizers take over now.
There are parallel sessions going on as well in LH1 and LH2. We are running 15-minute late for the conference. We are sorry for the delay. And the next speaker will be introduced by the chairperson, Professor Sudhir Gupta. Thank you.